Thermodynamics is the study of heat, and there are three major laws that we call the laws of thermodynamics. And it turns out that after the first and second law were discovered and written down, we realized that there was another, more fundamental law. So because it was more fundamental, we decided to put it first. And if you already have a first law, well, we call it the Zeroth Law of thermodynamics. And it says that if one object is in thermal equilibrium with another object, and it's in thermal equilibrium with a third object, then these two objects are also in thermal equilibrium with each other. And it might not be obvious, but this is actually the definition of temperature. If no heat is going to flow between these two, they're at the same temperature. If no heat is going to flow between these two, they're at the same temperature. And so if this one and this one are at the same temperature, no heat flows. That is the Zeroth Law of thermodynamics. Following that, we have a bunch of chemistry review we need to look at. So you did all of this in chemistry class, like what is temperature? You know your temperature scales, right? You know Fahrenheit and Celsius and Kelvin. You should know how to convert between them. You should also know and be comfortable with phase change diagrams. We have a variety of vocabulary that you need to know from chemistry that we're really not going to get into here. You can read them in your book, but we're not going to spend a whole lot of time reviewing chemistry because you already took chemistry. Some of this vocabulary is very easy, like Celsius and Fahrenheit, freezing point, boiling point, evaporation, condensation, etc., right? But for phase change diagrams, you should know like calories versus food calories. You should know calorimetry, conduction, convection, evaporation, radiation. All of these things, if they don't sound familiar to you, you're going to want to brush up. Now, let's take a look, though, at a phase change diagram. A phase change diagram is something that we introduced back in middle school, but you did more with them in chemistry class. And this is something, as you add energy, the substance will heat up according to its specific heat capacity, which we often just call heat capacity or specific heat. The substance will heat up, and then the temperature won't change while it melts. And then it will heat up again with a new specific heat capacity and until it starts to evaporate, and then it will level off again. Because evaporation and melting are cooling processes. They take energy to rearrange the molecules. If you don't believe me that evaporation is a cooling process, it's very, very, very easy to see. Okay? Take your hand, blow on it. Doesn't feel all that cool. Lick it. Now blow on it. Feels nice and cold. The evaporation itself takes away some of the heat. It absorbs heat into the liquid in order to rearrange the molecules and separate them further. There is math that goes along with a phase change diagram. When something is heating up, the amount of heat Q equals mc delta T. M is the mass, C is the specific heat capacity, delta T is the change in temperature. You can use Kelvin or Celsius here because it's change in temperature, so the fact that one has a different zero starting point doesn't really matter. But delta Q equals mc delta T, that's for whenever something is heating up or cooling down. If instead something is changing phase, you need to use the latent heat. So that would be the latent heat of fusion or the latent heat of vaporization, sometimes called the fusion enthalpy or the vaporization enthalpy. Probably not words we'll end up using in class. So the equation there is simply Q equals mL. The heat is equal to the mass times the heat of fusion or heat of vaporization. We will, of course, do some example problems using delta Q equals mc delta T and Q equals mL in the last video in this series. More chemistry review you're going to need to know are Boyles Law and Charles Law. You won't need to know Cole's Law, that's shredded cabbage with dressing. Okay, dumb joke. Anyway, so Boyles Law and Charles Law. Boyles Law is P1V1 equals P2V2. The pressure times volume of a gas remains constant at constant temperature. Charles's law is V1 over T1 equals V2 over T2. As you heat up a gas, it will expand. If you cool it, it will contract. We can combine those together to make what we call the combined gas law. P1V1 over T1 equals P2V2 over T2. We will make great use of that. And something that may or may not be reviewed is the ideal gas law. We use this quite a bit in physics. It's PV equals nRT. Pressure times volume equals the number of moles of gas times a constant times temperature. Now that constant is called the universal gas constant. It's 8.31 joules per mole Kelvin, and it is on your reference tables. PV equals nRT is really very related to the combined gas law. Think about it. If you divide the T over, you get PV over T equals NR. N is the number of moles, which for a gas in a sealed container, a balloon or piston or whatever is not going to change. And R is a constant. And so PV over T is a constant for any given gas setup. An extension of that is almost definitely not chemistry review, but it's what we'll leave you with in this video. If you want to look at gases instead of dealing with huge numbers of gases like numbers of moles, you need to know Avogadro's number as well, by the way. Instead of dealing with huge numbers of moles of gases, if you want to deal with gases on the molecular scale, instead of PV equals nRT, we can use PV equals capital N kBT. What is this? Capital N is the number of molecules of gas, and then Kb is something called Boltzmann's constant. Boltzmann's constant is simply the universal gas constant divided by Avogadro's number. And it's equal to 1.38 times 10 to the minus 23 joules per Kelvin. So there you have it. That is the chemistry review portion of Thermodynamics AP2 style. We'll get into some more new material in the next video.